am going to talk about the graphical representation of a discrete frequency distribution. The first diagram that I am going to discuss is called the bar diagram. How do I plot a bar diagram? Bar diagram is plotted by looking at, first we consider the values that the discrete variable is assuming. So here the discrete variable is assuming values 4, 5, 6, 7, 8. So maybe I can show you the table that I am referring to. So here capital X is the discrete variable, which is the number of study hours that a student is devoting in a week for a preparation of a test. Here capital X is taking 5 values 4, 5, 6, 7 and 8, and it is taking the frequencies 10, 10, 25, 13 and 5. After obtaining this table, we can plot the bar diagram as follows. On capital X axis, I am going to plot the values of capital X, which is 4, 5, 6, 7, 8. And on Y axis, we are going to plot the frequencies. So what do? We first look at the first value that capital X assumed, which is 4. On 4, I am going to erect a rectangle of the height proportional to the frequency that was there in the table. Frequency was 10. So frequency of value 4 was 10. So I am erecting rectangle of height 10 on 4. Similarly, again rectangle of height 10 on 5, because frequency here was 10. Now when it came to value 6, frequency was 11. Then when I came to values 7, frequency is, let us see what the frequency is. Yeah, it is 20. So for 6 it is 25, for 7 it is 13, and for 8 it is 5. So therefore here we have plotted drawn the rectangles on each value of capital X with the height proportional to the frequencies which are given in the frequency table. There are certain things that you have to keep in mind. The width of these rectangles that you erect on each of the values should be same. Whether small, if you take a broader width or a smaller width, doesn't matter, but the width has to be same. Secondly, the distance between these are called bars actually. These rectangles that I am talking are called the bars, which we are drawing on each value of the capital X variable with height proportional to the frequency of that value. So these should be equidistant. That means the distances cannot be different between the two consecutive bars. And few things we can directly see from here, that the value 6 is occurring the maximum number of times, and then followed the value 4 and 5 is occurring same number of times, and the least number of times where value 8 is occurring. That means the students who are devoting 8 hours of study is least, and the students by and large are devoting 6 hours of study in a week to prepare for a test. So by looking at this bar diagram or the graphical representation, we can more or less get an idea about how the frequencies are distributed over the different values of X, and also what is the maximum frequency, what is the minimum frequency, and things like that we can. So here I will always write study hours on the horizontal axis, because whatever we plot, that legend should be there, title should be there. Title of Y axis will be called frequency, and title of the graph will be bar chart for frequency distribution of study hours for a test. And this is very important. If you don't write these titles, then nobody can understand what your bar diagram depicts, and then they will be completely clueless. So at times it is not important to show the frequency table, but rather you can work with a graphical representation, which is more powerful means of getting your point across. But nevertheless, if you miss these this information on the titles of the graph, then you are not getting the purpose is not getting solved, let me put it this way. So second graph that we are going to discuss again for the discrete frequency distribution is stem and leaf plot. So here the stem and leaf plot is a way of organizing data into a form that makes it easy to see the frequency of different values. The stem is the left hand column that has the digits in tens place, and the leaves are listed in the right hand column showing all the ones digit for each of the 10s, 20s, 30s and 40s. Now, for example, if the observation is 43, then the number on the tens place is 4 and the number on ones place is 3. So, 4 will become the stem and 3 will become the leaf. So, this graph gives the shape of the frequency distribution. Let us first discuss the steps for making this plot, and then I will show through an example how we actually construct it. First of all, we will determine the smallest and largest number in the data, and then we will, generally it is optional, but it is advisable to arrange them in increasing order. So, the smallest first and the largest later. That is optional, but it helps in doing it like this. Second step is we identify the stems. Third step is draw the table with two columns. First column, the left hand column will denote the stem and right hand column will denote the leaf. And then we fill in the leaf data in front of the corresponding stem. Now, you can say that, ma'am, what is happening is that if we look at the double digit number, it is easy for us to say the example that I took 43. But suppose number is 143, then what is stem and what is leaf? If the number is 143, then stem is 14 and leaf is 3. So, leaf is always the number on the ones place and rest of it forms the stem. So, here like I have taken the numbers are 123, 134, 156. Here 12 in the first number, 12 is the leaf and 12 is the stem, and 3 is the leaf. Similarly, for 134, 13 is the stem and 4 is the leaf and so forth. Now, again another type of numbers, the numbers with decimals. If they are there in the data, then how do we represent them? So, if suppose the number is, observation is 13.7, then the number before the decimal becomes the stem and after the decimal will become the leaf. Definitely this graph has a disadvantage, or these plots have disadvantage, that it cannot be applied if the size of data is large. Okay. In that case, we have to resort to some other graphical representation, but so far we will work with the small data and tell you how to draw this graph. So, let us take an example. Suppose I am given this data 71, 43, 65 and so on till 96. We have to make a stem and leaf plot for this data. As I told you, we can see all the numbers are in double digits. So, the number on tens will be the stems and number on the ones place will be the leaves. First, as I told you, it is optional, but let us first arrange them in increasing order 43, 65, 71 up to 98. It makes it easy for you to draw this plot. Now, we will draw a table with two columns, mark the left hand column as stem and mark the right hand column as leaf. So, here see here, if I will show the picture shortly, but see the stem here is, first stem is 4. Now, there is no number with starting with 51, 52, 50 and so on, but we will still retain that stem, we will not plot anything there. The next stem will be 6, next stem will be 7 for these two numbers, for these three numbers stem will be 8 and for these three numbers stem will be 9. And we will plot the leaves in front of the stems. So, for example, for 8 I will write the number 2, 3, 4 in front of it, so that we understand that this 82, 83 and 84 is represented. So, this is the stem and leaf plot that we are going to obtain. So, here the first column is stem and the second column is leaf. As I have already mentioned, looking at the data, minimum number was 43 and maximum was 98. The stems are coming from 4, 5, 6, 7, 8 and 9. These are the numbers which are on the tens place. 43 number was the first number, so 3 comes as a leaf. So, there was only one number with 4 in 40s, which is 43, therefore 3 comes here. No number with 50s, so you leave this blank. Please do not put a 0 here. If you put 0, then it will make it 50. That means 50 is also an observation given to you, but you don't have any number starting with 5, 51, 52, 50 and so on. Therefore, you are just going to write the stem, but you are going to write no leaves. That means there is no number with 5 as a tens place. Then comes the next number 65, there is only one number, so 6 here and 5 here. Then there were two numbers starting in 70s, one was 71, other was 76. So put 7 here and write the leaves 1 and 6 in front of 7. Similarly, as I had already mentioned, there are 3 numbers in 80s, 82, 83, 84. So I put the stem as 8 and I put the leaf as 2, 3 and 4 in front of it. Similarly, for 9, I put the leaf as 5, 6 and 8, and they should, because we have arranged them in increasing order, so they are coming in a very proper form. Here you can, what happens in this plot is you can see how the frequencies are distributed. So you can, you can just see like this, the frequencies are distributed, that there is only one number is in 40s, there is only one number in 60s, but there are 2 numbers in 70s, 3 numbers in 80s and 3 numbers in 90s. And you can also, don't lose information on the observations. So you can also know what observations are there and how. So if you look at the frequency of, say numbers in 40s, then at 43 it will come once, then in number 60s, then 65 is coming once. If I am looking at numbers in 71 is coming once, but if I look at numbers which are in 70s, then there are 2 numbers in 70s and so on and so forth. So after deliberating on the graphical representation of the discrete frequency distribution, the next very important frequency distribution that we encounter in descriptive statistics is called the continuous frequency distribution. When do we apply this distribution? When do we obtain this distribution? We obtain continuous frequency distribution in 2 cases. First, when the variable is continuous variable. As I told you, as we have mentioned, the continuous variables takes real values, and when the variable takes real values, then we have to construct continuous frequency distribution. It can also be constructed for variables which are assuming integer values, although they will be like a discrete variable, they will be discrete variables, but if the discrete values are large in number, if they are very large, then what we do is we construct the continuous frequency distribution for that data also. So how do we go about it? Again, here what we do is, we will first look at the variable under study, and we will look at the data which is provided on the variable under study, locate the minimum and maximum observation on the variable. Say if I am denoting the variable by capital X, locate the minimum and the maximum observation on capital X, and then using that I am going to construct, or rather I am going to group the data, group the observations on capital X into class intervals. So here, instead of looking at 2 occurring 5 times, 4 occurring 6 times, I cannot do that. What I will do is, how many students have got marks between 0 to 20, how many have got marks between 20 to 40, 40 to 60, 60 to 80 and 80 to 100. So here, this marks of the student, which is the variable, has been divided into 5 groups: 0 to 20, 20 to 40, 40 to 60, 60 to 80 and 80 to 10, and these are called the class intervals. These groups are called the class intervals, and then we work with these class intervals and the frequencies of the class intervals to construct continuous frequency distribution. So before I go into the depth about how to make a continuous frequency distribution, we need to understand few terminologies. First is the range. So range is the maximum observation minus the minimum observation. You have to locate the maximum observation, you have to locate the minimum observation, and we will take the difference. The difference gives you the range, and range helps you in deciding how many class intervals you make. Number of class intervals that you make depends entirely on the student or the person who is constructing the continuous frequency distribution. Next thing is, whenever you construct a class interval, the class width comes into the picture. So here if I have a class interval like 120 to 130, then this 120 is called the lower limit and 130 is called the upper limit. So the width of this class interval will be 130 minus 120, that is the upper limit minus the lower limit, and here in this case the width comes out to be 10. Similarly, you can find the widths of the other class intervals, and we will talk about it a little later, that we need to have, generally we should have the same width of all the class intervals that we are considering. Next comes is the class mark. This is the most important thing that we do in the continuous frequency distribution. What we do is, we essentially look at the upper limit of a class interval and the lower limit, add them up and divide it by 2. The value that I obtain is called the class mark, and this class mark is the representative of that class interval. So what we have done is, we have grouped the marks between say 120 to 130. I have grouped the observations in the class interval 120 to 130. Then we have to have a representative, what represents best from when, because the value of variable is varying from 120 to 130 in our case. Here the value will be greater than equal to 120 but strictly less than 130. Those values will be considered in this class interval. So that will give you the frequency of the class interval 120 to 130. So now what is the class mark of this particular class interval? It will be 120 plus 130 divided by 2, which is 250 divided by 2, and by simple mathematics it is 125. Now next comes the frequency density. It is the frequency per unit width of the class. This is used only when you have a class of unequal widths. If the class are of equal width, then we never work with frequency density, we work with frequencies. But if the class intervals are given of unequal widths, then I have to construct frequency density of a class, which is the frequency of that class interval upon the width of the class interval. So class intervals will be given to you, frequencies of the class intervals will be given to you, and you can, by just dividing them up, you can find out the frequency densities, and they are essential to compare two classes of unequal width. That must be kept in mind, that unequal width is important. If the widths are same, then we never work with frequency density, we will just work with frequencies. Then comes the main, as I told you, that when we construct a continuous frequency distribution, the most important thing is to construct the class intervals. You can have 5 class intervals, you can have 10 class intervals, you can have 15 class intervals, you can have 4 class intervals for the same data. So there are certain characteristics that you must have while you are making a class interval. Whenever you make a class intervals, the classes should be clearly defined with no ambiguity. There should be no confusion between the classes. Then the class intervals should be exhaustive. That means they should cover the entire range of data. There should be no data point which is excluded if you construct these class intervals. All the data points can be associated with one or the other of the class intervals. Then these class intervals should be mutually exclusive and non-overlapping. Very important. You cannot have the same observation going into the two different class intervals. One observation can go into only one of the class intervals. So the class intervals need to be non-overlapping, and the classes should be of equal width as far as possible. And one thing I want to add, the class intervals should not be very small and should not be very large, because the analysis of this continuous frequency distribution or the interpretation of this continuous frequency distribution will be dependent on class marks, which are further dependent on class intervals. So if you have very few class intervals, then you are maybe underestimating the mean, and when you have a very large number of class intervals, maybe you are overestimating the mean, and the information gets too much scattered and you are not getting anything meaningful out of it. So therefore we must have something class intervals, by thumb of rule, let us say from 5 to 8 class intervals should suffice. So to take an example, suppose I have collected data of heights of 40 individuals, and the heights look like this. Okay, there are 40 individuals here, their heights are in centimeters. Now notice that here, as I told you, first we have to look at the minimum value. So 120 is the minimum value and 150 is the maximum value. So the range is 150 minus 120, the range is 30. To take care of this 30 range, I can have the class interval 120 to 130, 130 to 140 and 140 to 150. That means only 3 class intervals. When I do that, I am just reducing the class intervals too much. I am putting too much of frequencies into one class interval, and therefore I think the frequency representation will not come good. So I think that we should do, since the range is small, only 30, I will go 120 to 125, 125 to 130 and so on. That means classes of equal width and of width 5. And so something like this, the table that I have to construct. So there are going to be 3 columns. First column is class interval, which I have again said it is dependent on the person who is obtaining the continuous frequency distribution. There is no set rule, but by and large, say 6 to 7 class intervals if you construct, then it gives a better representation of the frequency of the data. So I have resorted to class width 5. So therefore, and the minimum value is 120, it must come in the first interval, and maximum value is 150, it must come in the last interval. So all the class intervals are exhaustive. They are all of same width 5 each, and they are non-overlapping. How they are non-overlapping? This 120 to 125 means all observations which are greater than or equal to 120 but strictly less than 125. That is why this is called the exclusive continuous frequency distribution. I exclude the upper limit. The upper limit gets included in the next interval. So here it will be the observations which are greater than or equal to 125 but strictly less than 130. Let me move back to the previous slide. So we had constructed the first class interval as 120 to 125. So see here, I can clearly see one is this observation 120. There are 2 123 here, they are also lying in that class interval, and there is one more observation 124. Mind you, 125 is going into the counting of 125 will go into the next class interval. So now I want to obtain the frequency of the interval 120 to 125. That means all the observations which are greater than or equal to 120 but strictly less than 125. So 120 gets included, 122, these two 123 gets included, 124 gets included, but 125, which is occurring many times, doesn't get included in this class interval. Therefore, the frequency is 4. So the frequency of the class interval 120 to 125 is 4, and then 125 to 130 is 11. We can do the counting and we can count the total number of observations which are greater than or equal to 125 but strictly less than 130, that will be 11, and like that we will obtain the frequencies, these 3 will be 6, and then between 1 and more greater than or equal to 145 and strictly less than 150 is 7. Slightly I think we should have gone for one more because we are not including 150 here. So anyways, this sum of these frequencies should add up to be capital N, which is the sum of the frequencies, and that will come out to be, actually there are total 40 is the total size of the data. So they will come out to be, the sum should come out to be 40. If it is not 40, you have to check the frequency of each of the class interval and again count. Maybe you have missed some counting or you have doubly counted. Then comes in the middle, we must also write or make a column of class mark. Here in this class mark, what I am going to do is, as I have told you, take the lower limit, take the upper limit, divided by 2. So like that I will get 122.5, 127.5 and so on up to 147.5. So 122.5 is a class mark of this class interval. It is a representative of this class interval. So in some sense we can think that 122.5 is actually repeating 4 times. Slight correction, I think I have been little bit hurriedly I have done. Last we must add one more class interval 150 to 155, so that value of 150 gets added in the next class interval, but I am sure you have understood the concept and you will be able to just do it.